Hi and welcome to MSc. In this video we're going to be looking at VSEPR theory, specifically the scenario where we have 3 electron domains around the central atom. When we have 3 electron domains around the central atom, there's 2 cases that we need to consider. I will do 3 examples to cover those 2 cases. The first case is where we have 3 bonding domains and 0 lone pairs. And this will be a theme as you go through these videos on various number of electron domains. Case 1 is always where all the electron domains are bonding domains. So we will have no lone pairs around the central atom. An example here is boron trichloride. And we can take a look at working through this by looking at the number of valence electrons that will be present. Boron is going to bring 3 valence electrons, and we have 3 times the 7 from the chlorine, and that will give us a total of 24 valence electrons. We can clearly see that boron will be here in the middle, right? And you might just naturally space out the chlorines, kind of space them around, because you know that they want to kind of spread out in space. Right? And then we'll put the electrons on the chlorine and we'll see what we have left. Again, you can use X's or you can use lines for the lone pairs. I sometimes find with chlorine that the lines in the L and the chlorine can kind of look a little bit similar, so just be careful if you're using that notation with chlorine. In this scenario, I've placed 2, 4, 6, and I've done the same here and here, so that's 18, 20, 22, 24. So that's all done in this case. So this is the Lewis formula or Lewis diagram. Again, I probably wouldn't in a picture for marks mix up my notation and use X's here and dashes in other places. But remember, whenever you draw a line in a Lewis formula, it's the equivalent of 2 electrons. It's either a shared pair or it's a lone pair. In this case, we can see here that the boron has an incomplete octet. And so while it doesn't obey our octet rule, the chlorine does in this case. Chlorine is much more electron negative, and it will pull the shared pair closer to it, and this will make a fairly stable structure. In this case, we see 3 electron domains around the boron. We see 1, 2, and 3. Again, an electron domain is either a lone pair, a single bond, a double bond, or a triple bond. They all count as a single electron domain. Now, from this arrangement of having 3 electron domains, in this case all bonding domains, there's some things that we can draw conclusions about. We know that the electron domain geometry is trigonal planar. That will be true for both cases here, first case and second case, because it's 3 electron domains. So that won't change. Trigonal is just a fancy way of saying triangular, and planar means that this is actually a flat molecule. The molecular geometry here is also trigonal planar. And again, that will also be a theme through these videos. When the number of electron domains matches the number of bonding domains, then the electron domain geometry, in other words, the geometry of the domains themselves, will match the molecular geometry, how the molecule is arranged in 3D space. And lastly, this will also have sp2 hybridization on the boron, the central atom. Again, this video's purpose is not hybridization, but it is good to point out the link there. 3 electron domains will lead to sp2 hybridization. There's a second example I'd like to do with the 3 bonding domains, and this is the HCOH example. And what makes this one unique, this is methanol, right? And it's going to have carbon with 2 hydrogens off of it, and it will have a double bonded oxygen here. Right? You can work through the number of valence electrons and reason that that's how it has to be here for this to work. It's not an alcohol because of the number of atoms here with trying to keep with the octet rule. So I'm missing 2 lone pairs here on the oxygen as well. So what makes this one different than this case here is that these 3 electron domains are all single bonds, whereas these 3 are not all single bonds. So go back to the previous example for a minute. A key piece here is that all of these bond angles are 120 degrees. They're all the same, spread out in 3D space. We can see this if we go over to a PhET simulation. So here we have the linear option with 2 electron domains like we've already seen, and I can drag in or click in a new bond, and I can see that this looks like it's a fairly flat molecule. I can go in and show the bond angles, they're all 120. I can add the molecular geometry and the electron geometry. So this looks very much like our boron trichloride. I can even click over to real molecules, and here I have boron trifluoride, not exactly the same. I don't think that's one of the options here in PhET is the chloride, but this looks very similar. And again, you can see it's a flat molecule. You can see the bond angles are all the same at 120. So how is this different than our other example? Well, here they're all the same, single bonds, so they all repel each other equally. In this new example, we have 3 electron domains still, because the double bond counts as 1 electron domain, but it exerts a bigger repulsion. So this bond angle in here is actually about 118 degrees. And this bond angle here and here, those are each 121 degrees. Again, there's more electrons packed into this double bond. We have both sigma and pi bonding going on in there. So we have 4 electrons packed into this space. That's going to repel the others and push them back just a little bit. Notice that doesn't change that we call it trigonal planar geometry of electron domains, and it doesn't change the overall shape. It just makes a slight distortion to our regular 120 degree bond angles. The second case I'd like to look at is the case of 3 electron domains where we have 2 bonding domains in 1 lone pair. And this is a pretty good example of this because sulfur dioxide is tricky to draw out. And you can trace out the number of electrons and try this, and you'll actually find that there's 2 pictures you can draw. What's cool about this is you can tell which one's correct by using something called formal charge. That's not the purpose of this video. But either one will still have the same geometry. And the correct picture is actually with a lone pair on the sulfur and 2 double bonds coming down to the oxygen with lone pairs on it. And so we see here in this scenario the fact that we have an expanded octet here on the sulfur. The oxygens obey the octet rule. Sulfur here has kind of quasi-control of 10 electrons. Although we know that the shared pairs with the oxygen is a bit of an electron bully and will pull some of those electrons in the shared pair closer to them. The other option here is having 1 oxygen with a double bond and 1 oxygen with a single bond with an extra lone pair. And when you do the formal charge calculation, this one is what it works out to be. So this is 3 electron domains because we have 1 here with the lone pair, we have 1 here, and we have 1 here. So there's your 3 electron domains. So when we compare this one to the previous example, well, because it's 3 electron domains, it'll still have an electron geometry that's trigonal planar. So these 2 double bonds and this lone pair are still arranged in the same overall 3D shape, right? A flat triangle. The molecular geometry is different though because there's no atom up here above the sulfur to really give it that trigonal planar shape. We have a lone pair sitting there. And so instead we call this shape bent or V-shaped. And lastly, there is no change to the hybridization on this sulfur atom. It is still sp2 because of the 3 electron domains. Again, we can go to PhET and take a look at sulfur dioxide. And you can see it here as a real molecule. You can see the lone pair sitting up top. You can move it around, see that it still kind of has that flat overall geometry, but you can see that it's bent. And you'll also notice here now that it has an angle less than 120 at the bottom. And that's because this lone pair has a larger charge density and it's going to push these double bonds towards each other a little bit. Now they offer a good amount of pushback because they are also highly electron dense as well, with 4 electrons in the 2 shared pair on each side. And again, this is a great simulation through PhET, University of Colorado. You can play with it and look at a lot of options here. If I go to the model and click away from the real, you can see the model says it's 120. It's when we get to the real scenario that we see here that it's less than 120. It's actually 119. So I'll add my label here as 119. I don't think you need to memorize these angles, But I think it is useful to appreciate that this lone pair pushes on those. And I would say if I was labeling this and couldn't remember the actual value for the test, I would say it's slightly less than 120. I hope this quick run through of 3 electron domains and VSEPR theory has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you so much for listening and watching.